We previously proved this theorem, that A dot B is equal to magnitude A, magnitude B, cosine of theta. That was proven already. We're going to use that theorem and another theorem to prove. The theorem that we want to prove is that vector A and vector B are orthogonal if and only if, and when you have if and only if, you use two F's, if and only if vector A dot vector B equals the number 0. This is a diagnostic theorem, a theorem that we can use to determine if two vectors are indeed orthogonal. In an if and only if proof, you have to do two things. You have to start with one side, let's say this side, and assume it's true, and then conclude the second side. But because it's if and only if, you also have to start with the second side and then see if the first side logically concludes from there. So we're going to prove this theorem that we just stated. So I'm going to use this notation which says we're going to go in the first direction. This is true, we have to assume this. So we're going to start off and say A and B vectors are orthogonal. And by definition, so therefore, theta equals pi over 2. Therefore, the cosine of theta also, will have to equal 0. And therefore, the magnitude of A times magnitude of B, cosine of theta, is also equal to 0, and therefore A dot B is equal to 0. So we were able successfully to start with 1 and go with 2. So now the question is, and I'll put these arrows this way indicating its direction, we're going to start with 2 and see we can conclude 1. Okay, here we go. So we're going to start off by assuming that A and B dot product is in fact equal to 0. Now there are two cases to consider now. Case number 1. Vector A or vector B, or both, are equal to the 0 vector. And if A or B are equal to the 0 vector, then automatically vector A and vector B are orthogonal. Now why is that? Do you recall the definition of the 0 vector is parallel and orthogonal to all vectors? So that's by the definition of the 0 vector. In case 2, both A and B, neither of them are equal to the 0 vector. So that's saying that the magnitude of A is not equal to 0, and the magnitude of vector B is not equal to 0. But we know that the magnitude of A times magnitude of B times the cosine of theta has to equal 0, and since neither magnitude is equal to 0, we conclude that the cosine of theta has to be equal to 0. And since the cosine of theta has to equal 0, and theta is between 0 and pi, we know that theta has to equal pi over 2. And since theta equals pi over 2, by definition, we say that A and B vectors are orthogonal. And so we're done. We have proven. I'll look at a couple properties here. We're going to pick one and prove it. The first one says that a vector dot itself is equal to the magnitude squared. And then the second one looks like commutative commutative property. The third one sort of looks like distributive property. And in 4 we have a scalar that can be assigned to any one of the quantities there. And the last one is pretty self-explanatory. We're going to prove property number 3. We're going to prove this kind of distributive looking property of the dot product. So it looks like this. Okay, we're going to use components to prove it. So we're going to say that vector A dot vector B plus vector C will equal, and I'm going to write it out in its components, dot, now vector B plus vector C is going to be the sum of the corresponding components, B2 plus C2 and B3 plus C3. So now if we use the definition and multiply corresponding components and then add, we're going to have A1 B1 plus C1 plus A2 B2 plus C2 plus A3 B3 plus C3. Now since these are scalar quantities, I can distribute ordinarily, and so I have A1 B1 plus A1 C1 plus A2 B2 plus A2 C2 plus A3 B3 plus A3 C3. Now if we order these around a little bit, we have A1 B1 plus A2 B2, that's this one and this one and this one, plus A3 B3, then the rest of them, plus A1 C1 plus A2 C2 plus A3 C3, it's a C3, then we have this quantity here, which we know to be A dot B, and we have this quantity here, which we know to be A dot C. Therefore, we have demonstrated.